I mean, if I took my silly putty and I stuck my thumb in it, you get an indentation. If I calibrate my thumb with a certain force and I measure the depth, I could get a hardness of the silly putty. Okay, you do the same thing with steel, only use a diamond. You might use 150 kilograms as the load on the diamond, and you'll get a penetration that's about 1/2 millimeter deep or so, depending on the hardness of the steel. And then you change it from a diamond to an 1/8 inch hardened ball, steel ball, or you change the load to 60 kilograms and you get a different hardness scale. So we have hardness scales going all the way down to rubber and plastics. PEX actually is reasonably hard because it's cross-linked. Hardenability, on the other hand, is how fast can you quench it to get this martensite, which is very strong, okay, and has hardness, but how deep will that penetrate into the steel? If you just have plain old carbon steel with nothing else in it except some manganese, then you're not going to get very great depth of hardenability. It might be 1/8 of an inch or 1/4 of an inch, depending on how thick the piece is and how well the fluid can quench that big chunk of steel or that thin piece of steel. But if you add alloy content, if you add enough alloy content, if I start making it out of a surgical stainless steel like this used to be 25 years ago a $300 pair of scissors. Probably be worth about $50 if it wasn't being sold to a doctor in a hospital, and it has to have an extra couple of $100 worth of life of insurance because they sue doctors all the time. Anyway, that's a stainless steel. When we get to stainless steels, I'll tell you which type is, but it's a martensitic stainless steel, and you can heat that up and harden it, and you can just take it out of the furnace and let it cool in the air, and it will harden. It's called an air hardening steel. In fact, the only way to get that annealed if you heat it up is to leave it in the furnace and bring the furnace down very slow, like over days, not days, but over 10 hours or 5 hours or something. That will harden up. It would take an hour to transform that, typically, okay? Or to not transform it, okay? So you can air harden it, take it out of the furnace, it cools down in 2 or 3 minutes, and you get full hardness, okay? So you have a tremendous range, but that thing's only about 80% iron. It's got 20% alloying elements, and it's gonna cost you 5 times as much as a piece of carbon steel, okay, to buy per pound. So you can add hardenability, you add cost. Any questions on that? So we can pass this out. If you just showed up, there are some other big handouts out there. The big handouts are for the fusion welding module that you're supposed to watch online. It is online. I've got a student who's loading it onto YouTube, which will be easier for you to access. If you don't have an MIT, if you have an MIT connection, it takes, for each hour-and-a-half lecture, it might take 2 minutes for it to download. And it has to download the whole hour and a half, and that takes a couple of minutes if you have a fast connection. If you're at home and you have a slow connection, it could take a half an hour. So the students last year decided I should put my lectures on YouTube because it will, download part and it will keep on downloading, so you get kind of continuous. So you only have to, you have to wait 30 seconds for YouTube to start up. So we're doing that, okay? We're putting it on YouTube. Now, there are a number of problems, and that's what I'm handing out is something from a welding textbook, welding metallurgy textbook. In fact, I brought with me a number of welding metallurgy textbooks. Just went to the shelf and pulled off 6 books on welding metallurgy. So here's one on welding metallurgy just of stainless steels. Here's one on just of nickel base alloys. Here's a metallurgy of welding in its 6th edition by this guy in South Africa. He doesn't have a whole lot else to do in South Africa except write extra editions of his book for the last 40 years. He's more of he actually sort of a physics background, but anyway, there's interesting stuff in here. Here's one on Welding Metallurgy, written by Sindo Ko, who's a professor at University of Wisconsin, graduate of this department, worked with Professor Flemings. A lot of solidification in there because he did his thesis on solidification. I've already showed you Stout and Doty, which is 4th edition, back in 1980. Okay, and this is actually where this, or actually that chart may have come out of Sindo Ko, or either that or it came out of Easterling. Easterling was Swedish. He's passed away now, but he wrote this book on the physical metallurgy of welding. And I suspect in one of the 2 modules you'll read, I do a case study right out of Easterling on the Alexander Keelan disaster. Anybody know what the Alexander Keelan was? It was about 1980, and in the North Sea they were drilling for oil. This is sort of the beginning days of drilling for oil in the North Sea. And they had a production platform that was supposed to be a drilling platform, but they converted it to a hotel. And it was a 250-bed hotel in the middle of the North Sea. And one night in a North Sea storm, which they're sort of famous for North Sea storms, it had 5 legs, and each one of the legs was about 20 feet in diameter. So think of a mini submarine leg, okay? Not the same thickness because it didn't have to go the same depth, but nonetheless, they had a fatigue crack that started at a weld defect. It was all made in a shipyard in France. And the story is basically, for all their production welding of the legs and everything, they had very tight welding procedures and process control to have low carbon so they get low hardness. But then they had their maintenance people go and mount hangers. Well, the maintenance people didn't have the same type of welding procedure requirements and supervisors, and so they just went out and got a piece of pipe. They were going to put a hydrophone on it for when they were doing some of their drilling, and they welded on this 6 or 8 inch pipe, and it turns out to be a medium carbon steel, had very good hardenability and hardness, and it ended up getting a hydrogen crack that was, originally about 1 inch long. And that thing grew and ran for about 50 feet, ran all the way around one of the 5 legs. You lose one of your 5 legs, and in a storm, the whole thing came down. A couple hundred people lost their lives. There's all kinds of studies by the Norwegian government about safety and all kinds of things about how to improve safety on jack-up rigs. Okay? Yeah.
How long does a hydrogen crack like that take to develop?
Well, the hydrogen crack is going to grow within the first couple of days after welding, because remember the CO2, the Sprite example, okay? But for the fatigue crack to grow, it was probably 1.5 years or something. It's in the book. But for a fatigue crack to grow 50 feet or something, it is growing with the waves, every wave that comes by. So the number of cycles is millions and millions and millions, but to grow that far. However, the growth rate of fatigue crack, there's a very rough rule of thumb that, well, if you look at the time, let's see, versus crack length. For a fatigue crack, we know from fracture mechanics and other things that the crack growth rate goes like that. It actually goes in the mid-range. It goes with the number of stress cycles to the 3.5 power. Hey, isn't that great? We know we can quantify things like that. That's what people at universities do. That's called the Paris Law, and Paul Paris is a retired professor at Ohio State University, and he is one of the most arrogant people you'll ever meet. He's not the most arrogant I've ever met, but he's in the top 5. Okay. Other than that, he's a nice guy. So the fatigue crack rule is sort of, the fatigue crack grows 10% of its length in the first 90% of its life. And then it starts really going fast, okay? So it grows the last 90% in the last 10% of its life. It's a rule of thumb, maybe it's 80-20 rather than 90-10, but in fact, you got to find the fatigue cracks when they're still small. So this one, they probably could have found it, if they had found it when it was only a foot or two long, grew to 50 feet, they would have been okay. But when it gets to be 50 feet long, goes all the way, nearly all the way around a 20-foot diameter leg, it's not hard to understand why the leg falls down, right? But for all you divers out there, they had just done a diving survey to look for cracks 2 weeks before. So do you think they missed it? Yeah. Okay. That was one of the problems. Okay. You know, a lot of times, now these are commercial divers, not Navy divers, right? You guys are responsible. But some commercial divers, hey, it's cold in the North Sea. It's much easier to just go down there and come back up. Why bother to look for cracks, right? While you're down there. Well, the North Sea is only like 200 feet deep. So it wasn't that deep. But when you got, you know, 50-foot waves, it's hard to survive. And well, the real reason, they actually had the right type of lifeboats and everything. I'm not sure if they had enough. I have read some of these stories. And these were lifeboats that were, you know, they had tops on them so that they could be completely swamped, right? Except they didn't have a good enough communication system. It happened in the middle of the night. People were asleep. Some of them got launched too early. It's sort of like the Titanic, you know. They had enough lifeboats, they just didn't have them in the right place at the right time, okay?
Yeah, I know a guy who was a commercial welder
Yeah.
up in the North Sea when they were building all those oil fields.
Yeah.
And I'll ask him about it if he knows anything about it.
Well, I mean, you can read it and you probably, I don't remember which module I kind of gave that as a case study. But they had all kinds of safety rules that came out of that about oil rigs and tipping over and stuff. And of course, and it also, I think it had to do with flooding of one of the legs. You lost one leg and then you had another leg got flooded because they left a hatch open or something, okay? And so when it tipped over or something, you had all this water on the inside that it wasn't supposed to be bearing that weight. Well, and they had all kinds of things about you got to close the hatches and things. Well, 4 years later, off Brazil, Petrobras had a similar failure, and there's nice pictures for 3 days in the nice sunny weather. There's this, I used to have, well, actually I have it on one of my old computers. I can't remember the name of it. But if you start looking up oil rig failures, there's a nice picture of this thing listing at about 45 degrees, you know, this $500 million oil rig out there listing at 45 degrees. And there was nothing they could do. Everybody got off. You know, no one died in that one, but they left a hatch open, okay? And anyway, so, hey. So there's a reason why you're supposed to yell at people if they leave hatches open, right? Okay, which is actually also the reason why the Titanic went down, right? It was unsinkable and had all these compartments, except the gash went for 6 compartments along the side, and it could tolerate like 4 compartments flooded. But when you have 6, they didn't just, who would ever expect that they could gash 6 compartments, you know, the length of 6 compartments. But anyway, sort of similar to this guy in Italy who kind of went close to the rocks. Oh yeah. I mean, the failures just keep coming back, right? Anyway, so here we have, you know, there was a philosopher at Harvard named George Santayana who is famous for a quote that those who do not remember the past are condemned to repeat it, right? So, anyway, so here are typical welding problems as listed by one of these welding handbooks for steel, okay? And porosity, well, you folks have probably seen porosity before in welds. And I'll pass this around. This is something by the British Welding Institute they put together 30 years ago and shows different types of cracking. Someone here, I'm sure they have porosity. Here's some surface porosity. Right here, here's an X-ray with some restart porosity. They restarted a weld and you get porosity. Here's a crater pipe, and then you got micro porosity. So there's all kinds of, and there's other cracks in here, you can pass that around, but this is something to train inspectors sort of the types of defects you can expect in welds. Porosity is not usually a problem. The structural welding code allows like 6 1/8-inch pores for every foot of weld, okay? So every 2 inches you can have a pore. Porosity doesn't have sharp edges. It's not sharp like tearing that piece of paper. It's like the hole in the piece of paper, you know, that you punch in the paper. and it doesn't weaken it as much. It does weaken it, but not as much. And you usually have enough toughness in steel. And so you have to control the deoxidizers and things. Hydrogen cracking, we're going to spend a fair amount of time on. Lamellar tearing, something that occurred in steels back in the days when we had higher sulfur, like when I started. Typical sulfur content of a steel made in the United States in 1970 was 0.025. The specs might say it has to be less than 0.040, which means that spec was probably written in the 1940s. Or some ASTM specs still say it has to be less than 0.050, which means that spec was probably written in the 1920s. And it hasn't changed for almost 100 years, okay? When I was an engineer at Bethlehem Steel, the Japanese were selling A36 steel, it was just simple I-beams with 0.005 sulfur. Bethlehem Steel was trying to get an extra $20 a ton, trying to charge an extra 8% on the steel to give you low sulfur. The Japanese, everything they made was low sulfur. They couldn't give you 0.025. So today we actually have, in general, 0.005 sulfur in our steel, but 30, 40 years ago we didn't in the United States. They did in Japan. If you went back 50 years ago, they didn't have it anywhere in general, unless they went to very expensive processing. Lamellar tearing is basically you get sulfide and oxide inclusions, and they get rolled out in the plate, and it's like having a piece of steel plate that's like a sheaf of paper, and it's laminated, okay? And you get hydrogen in there, and it just separates just like a sheet of paper would, right? I mean, I can take a pad of paper and you know, fan through the pages, okay? Well, lamellar tearing, you get the stresses of welding, you get hydrogen in there, and you'll get nice tears, and there's pictures in that book of lamellar tearing. Reheat cracking, this is if you're stress relieving a pressure vessel, and if you have, particularly if you have vanadium in your steel and an alloy steel, you can get carbides precipitating at grain boundaries, and you need to be careful of the composition of the steel. We learned 40 years ago how to correct most of this. My second boss up when I worked in industry had done his doctoral thesis on this, and they sort of learned how to solve the problem in the 1960s. Solidification cracking says keep proper manganese to sulfur ratio. Well, this was a problem back in 1920, okay? When we had high sulfur, like 005 sulfur. The proper ratio, if you go back and read a metallurgy text from 1920 or 1930, is the manganese to sulfur ratio has to be greater than 6. Okay, well, if I have 0.05 sulfur, 6 times that is 0.3 manganese. And most steels have 0.3 manganese. Many of them today have 1% manganese, so it's not really a problem. Unless you're doing something like the Mass General subway stop, and they're doing that. I told you, they call me up and I say, what's the composition and stuff. I would also, when I was doing some of this stuff, if it's a 1900 piece of steel, I would also start worrying about, the manganese to sulfur ratio. It wasn't just what's the hardenability and the hardness. I would start worrying about some of this in the really old steels. But in general, this is not a problem. Although I did work on this problem. Bethlehem Steel owned shipyards when I was in the research lab, and they wanted to weld over primer. Anybody been in a shipyard where they wanted to weld over primer? They do. This comes up about every 3 to 5 years, because ordinarily in a shipyard, you get pre-painted. They bring in the plates from the steel mill. They put them in a yard. It rains on them. They get all rusty. They take them into the panel shop, and they shot blast them to get all the rust off. Okay, and then they paint them. Well, now you can't weld over paint, because the paint will cause the solidification crack, in part because the paint has got a lot of phosphorus in it for corrosion protection. And phosphorus will cause solidification cracking. So one of my first projects was to, well, Tom, how can we come up with a weld metal that can weld over paint? Well, people have been trying to do this for 50 years. No one has solved the problem, and I didn't solve it either. So, okay. Actually, what people have done is they've gone to different composition paints, but it still doesn't work very well. When I was in Japan in the 1980s visiting shipyards, they were trying to do it. I was up here at Bath Iron Works. They were about 8 years ago. They were trying to do it. But in general, the best thing is just, you know, grind the paint off for 3 inches on either side and weld it and then repaint it. But then sometimes those paint jobs aren't any good, and that's why we see the corrosion pictures you folks have been showing us, okay? A lot of times it starts in that repainted area because it's not as good a paint job. Low heat effective zone toughness, you use low heat input. Yeah, well, this is if you develop a proper welding procedure to begin with. It's not usually sort of a continuing problem. Low fusion zone toughness due to coarse columnar grains. Again, this is sort of, you choose the right steel chemistry to begin with. You get the right welding procedure, you shouldn't run into these things. So if I look at all these things that some welding engineer put together, really the only one you really have to worry about is hydrogen cracking. In terms of everyday, you know, someone fooling around with things. And so Tom yesterday is talking about welding underwater, and certainly if you're wet welding, you are generating hydrogen. If you're wet welding, that arc is about 60% hydrogen, because you're breaking down the water into hydrogen and oxygen. So you have carbon, hydrogen, and oxygen. And actually, I probably ought to give you an hour lecture, since we have so many divers or former divers or whatever, on underwater welding. But one of the things I was thinking of, you said there's one company, Brokow or something? Brokow. In 1980, I was over at the Paton Welding Institute in Kiev, which is the world's, well, it probably still is, the world's largest welding institute. It has 5,000 or 10,000 people. And Paton's father, I think Paton has now passed away, but his father had been a hero of the Soviet Union under Stalin in World War II because he weld repaired the armor on tanks and got them back to the front to kill those Germans, right? And afterward, so he was a welding engineer in Kiev, and after the war he started, I don't know if it was before or after, but they named it the Paton Welding Institute. And the way they gave out money under the Soviet system is they had a Soviet Academy of Sciences. We have a U.S. Academy of Sciences, but they don't, Abraham Lincoln formed them. They're a quasi-governmental agency. They're right near the Lincoln Memorial on the mall in Washington. But they're really a private organization, but they get a lot of research support out of Congress and the Defense Department. That materials for 21st century defense needs, that was a National Research Council Academy of Sciences study. And Congress, if they've got some concern about some environmental problem or climate change or something, the National Academies will do a study. They'll get people to volunteer. They don't pay anybody. They have a full-time staff, but they don't pay any of the people on their committee. So they ask people at universities and in government and industry to come sit on these studies. And they do it for free because it's prestigious to be on a National Academies panel. Ultimately, you can never conclude anything because they all have to go through a peer review that just sanitizes everything. That's why they're quasi-governmental, right? In any case, but the Soviet Union, they had, I don't remember, 7 or 10 members of the Soviet Academy of Sciences, and they gave out all the research money in the Soviet Union. It's sort of like you take the Department of Defense 6-1 budget and the Department of Energy. I mean, these guys had billions of dollars to give out, and they would give a certain amount to each of the provinces, or whatever you call them, republics. I guess it was Soviet Socialist republics. Anyway, so Paton's son, who became the head of the Paton Institute, was on this panel of 7 or 10 people, and he was from the Ukraine, which was the richest of all the Soviet republics. Had 50 million people, and productivity was much better. So he controlled all the money for the top level that came to the Ukraine, and then he was president of the Ukrainian Academy of Sciences, which divvied up the money once it got to the Ukraine. Okay, so turns out his institute was a very big institute and very well funded. So when I went there in 1980, and we may talk about some of this when we get to titanium welding, I got to talk to their titanium welding expert, who was really the guy who taught them how to weld the Alpha submarine. But they gave me demonstrations. One of them was underwater welding. And in the Soviet economic system, the money didn't get divvied up on economic bases, it got divvied up on political bases. And so someone with a fair amount of clout at the Paton Institute was really interested in underwater welding. And they showed me a wet weld. I mean, I saw the weld made, and then he took it out of the water, and it didn't look like some dog had just left this on the sidewalk, okay? It actually looked like a regular weld, and it was a beautiful weld, okay? We didn't have anything like that, okay? Now, it still is going to be full of hydrogen, and some of the weld chemistry is going to be different and everything, but it was a beautiful weld. Well, when peace broke out in the early 90s, the Soviets were looking for capital, or the former Soviets, and there were all these ads, and there were the American Welding Society went over to Kiev to talk to the people at the Paton, and one of the big things is they were trying to sell their technology on underwater welding. I'll bet you money that Broco was the one who eventually licensed the Soviet technology. They were light years ahead of anyone else in the world on making welding electrodes for underwater welding, okay? So, I mean, and the same type of thing on titanium, okay? They just, for whatever reasons, it might have been a political, military reason, but they had this guy, Gurevich, who had all kinds of funding to weld titanium. In the meantime, David Taylor in Annapolis had a little welding lab, and they were welding titanium. And I can tell you the story when we get to it of building the Sea Cliff and stuff, which was like the Alvin submarine, but this was about 1980, and how they couldn't do it. With all the technology that David Taylor had produced, they really couldn't do it, okay? And they had to go to another process. Okay, so now, yesterday, I guess I handed out yesterday this plot, right? Didn't I hand out phase diagrams yesterday? I think this particular phase diagram. So this is a phase diagram of the iron hydrogen system. We want to talk about hydrogen cracking. And this is temperature, this is 100% iron, and this is weight percent hydrogen. You don't put hydrogen is very light. So down here they also talk about cubic centimeters of hydrogen per 100 grams of iron. Okay, well they use that unit because you basically take a sample of iron that's got hydrogen in it just after you weld, and you weigh it, you put it in a machine that's going to drive off of that hydrogen by heating it up, and you measure the hydrogen, and that's how they measure it per 100 grams, and they normalize it to 100 grams of metal that you put in there. You saw how fast that stuff comes off. I had a student who actually timed how long it took from making the weld to getting it into the analyzer, and you can lose half your hydrogen in the first 2 minutes, and it's very difficult to actually measure it. So no one's really measured. You can back calculate how much hydrogen was there originally, but you can't really measure it because it comes out so quickly. But the point is, I'm looking at this graph. Also up here there's anyway, turns out cubic centimeters of hydrogen per 100 grams converts to parts per million with like a 1.02 factor or something. It's almost exactly the same. So even though this one's cubic centimeters of hydrogen per 100 grams, which is what the analyst comes up with in the chem lab, it's almost the same as parts per million. I prefer to talk about parts per million. It's a little more scientific, okay? Actually, this is parts per million. This should be parts per million. I have to think about, this is parts per million by weight. Okay, so this is 0.28, yeah, okay. So anyway, 30, so this is about 30 parts per million right here. This is atomic percent, this is weight percent. So this would be parts per million by weight. So when we talk about parts per million, we're talking about by weight. In any case, this is 30 parts per million roughly. That's the solubility of hydrogen in liquid steel. When you solidify, it drops to about 10. And so you want to lose 2/3 of it. You're oversaturated by a factor of 2. Everything's at equilibrium. But things aren't at equilibrium. When you're underwater welding and your atmosphere is 60% hydrogen, Well, in theory, if you look at equilibrium thermodynamics, 60% hydrogen, you should only get about 70 or 80% of the amount of your 1 atmosphere. This is for 1 atmosphere of hydrogen in your shielding gas. Now, if you're down 300 feet, you can get even more hydrogen. Isn't this great? Because you have a higher pressure, okay? But this is all 1 atmosphere. So hydrogen gets worse as you dive deeper. It also, it gets worse, but the reason it really gets worse is the arc. It's not diatomic hydrogen, which is what this is. It's monatomic hydrogen because the heat of the arc dissociates the diatomic hydrogen into monatomic hydrogen. And I didn't bring it, although maybe I can find it in Sindo Ko's book. There is a plot that's been generated, if I can find Sindo's book, of the difference between the solubility of hydrogen in monatomic and diatomic hydrogen. Well, let's see. I might find it. Well, no, probably won't find it that way. No, that's worthless. He gives me the indexes. Well, I won't find it right now, probably. Maybe I'll find it at the break. But it turns out you can dissolve 50 times, roughly, depending on the temperature, the amount of monatomic hydrogen as diatomic hydrogen. And the bottom line of all this is you can dissolve from a welding arc lots of hydrogen into the weld metal. Even more. Turn that off again. There's a little button here that I hit every now and then. Even more than 30 parts per million. Okay, that's not a good thing. It turns out that if I start looking at the steels, I put this up earlier. If I look at full restraint, what do I mean by full restraint? Well, when you weld steel or aluminum, this actually was done for aluminum. Okay. This comes out of Sindo's book, I think. And you have a large angle, you get lots of distortion because as the aluminum shrinks 6% on solidification, the steel shrinks like 3.2% or something on solidification. So aluminum distorts more than steel because it shrinks more, but if you put in a V-shape weld, which you need for access to get the heat down to the bottom, you'll end up shrinking more at the top and you will end up with something that distorts. You can change the angle a little bit. If you have no angle and you do an electron beam weld, you can get almost no distortion, but you can't do electron beam welding all the time. So you have a distortion problem. You can do all kinds of things. If before welding you have a double groove weld and you weld everything from one side and then go back to the top, you'll end up with lots of distortion. If you balance your weld one side, then the other side, then fill up that side, and then fill up the other side, you can balance it and get rid of your distortion. Okay? In fact, I had a student, my very first student was a bachelor student in 1977 or no, 78. He graduated and he went to work for a company called Electric Boat. And one of John's things in the 1980s is they used to make submarine tubes, these long tubes, the torpedo tubes on the submarine. And I don't know, they're like 30 feet long or something. I don't know exactly how long they are. And they have to be very straight. And so they'd weld these things together, they'd have distortion, and they'd have to go in there and bore this thing out, machine it. Okay? And John taught them, well, they could weld the circumferential welds, and if they actually, so you'd be welding right here, and you put a little dial indicator up there as the thing's going around in circles, welding, you're rotating the whole pipe, and you have a little dial indicator at the far end, and you can see when it's going out of the center line. It's distorting. And then what he would do is he would kind of monitor that while they're welding, and he'd come back in and he would change where he would start the next weld on the next pass. This is a fairly heavy wall tube, okay, and to try to bring it back to the center line. And if he couldn't do it, he would actually go in there and grind out part of the weld and re-weld it to bring it back, okay? And so he could weld those things by being careful, monitoring it as you go to control the distortion. So all they had to do was a skin pass and welding to clean the thing on the inside, okay? So you can do things to control the distortion. But in fact, if you have a very highly restrained system, big heavy plate and egg crate type construction, and you have this in all your tanks and and stuff you build inside whether it's surface ship or a sub, you have a lot of restraint, and the material can't distort. You put that last panel, you put the top on a 6-sided box. That last 6 panel has nowhere to go because the other 5 panels are sort of holding it in place. So the distortion is not distortion so much as it is residual stress. You can trade distortion versus residual stress. And so, I don't know if I have it, probably don't have it on this thing, but it turns out if you're welding sheet metal less than 3/8 of an inch thick, you don't get a lot of residual stress. If you have something 1/8 of an inch thick, it's almost impossible to get residual stress because the thing is so flimsy, it can't support a lot of stress. I mean, it's a beam, and the beam is so thin, it basically relieves its own stress just by allowing a little bit of bending in the sheet metal. The sheet metal may not be perfectly flat, but it's good enough. If you're 1 inch or 1.5 inches thick, it's so rigid, the plate is so rigid, you don't have too much distortion most of the time. You have lots of residual stress, and you can have yield level residual stresses, the maximum stresses you can get in the weldment when you're a thick plate, like 1 or 1.5 or 2 inches thick, which is something that you do in submarines. The absolutely worst situation for distortion is somewhere in between. No distortion when you're thin because the plate itself is flexible or the sheet is flexible. No distortion when you're very heavy. So distortion can be a problem, but if you weld sequence properly on submarines, you can control it. The absolutely worst situation